Okay, let's look at these multivariable functions and look what it means to be taking a derivative of these functions. Here we go. Okay, so just a quick reminder, in single variable calculus, the derivative looks something like this, right? If you want a derivative at value a, we see what happens with the function when you look at a point nearby and then see the rise over run between these points. So you look at the difference in the height by looking at the difference between f of a plus h and f of a. And then you divide by the amount you changed the x value by, so h here. And you're taking the limit of what happens, what slope does it get closer and closer to as h gets closer and closer to 0. Okay, so this is the formal definition of the derivative in a single variable calculus setting. So what to do when you have multivariable functions? Well, I guess we could do this change a little bit and looking at the difference quotient, like, but do it for each derivative separately. So if you want to talk about what's called the partial derivative, so it's called partial derivative because it's not the full story of the derivative, right? You're only changing one variable at a time. So this is the partial derivative of f, and it's very important to specify which variable you're taking the derivative with. So if you have a function fxy, you could be taking the derivative with respect to x, and you could be taking the derivative with respect to y as well. And then you'll have two different derivatives. You could have a situation where derivative is positive in one direction and negative in another. So the definition of the derivative itself looks like this. So this is first for the variable x. So the notation we're going to use, there's actually lots of different notation. We're going to use subscript. So if you write f sub x, this means we're taking the derivative of f at the point AB in the direction of x. That's what that means. And what you do is you're going to do the plus h thing, but only to the x variable. And you're still going to subtract without the plus h, and then you divide by the amount you added, which is h here. So this is partial derivative of f with respect to x. And there's a lots of notation here. So let me just list them. I want you to be able to be familiar with all of them. So here we go. So subscript x. Sometimes if there's lots of variables, you might just specify which variable it is. So x is the first variable. So f sub 1 could be another notation for this. Sometimes people use capital D with the subscript x. So this is the derivative in the direction of x of f. This is very similar to Leibniz notation. So in single variable calculus, you sometimes write something like this, df dx. You just make the d curly. So it looks like the number 6 that's mirror reflected, right? So del f over del x, that's what this is called. So that's partial derivative of f with respect to x. And sometimes people just write del subscript x of f. They all mean exactly the same thing. And you could also take the derivative with respect to y as well. So if you write this, then you're adding h to the y variable and then doing this limit thing. okay? And kind of corresponding notation for this is f sub y or f sub 2 because y is the second variable here, d sub y, del f, del y, and so on. So I hope that's not surprising. Let's do some examples. Okay, so how do we compute this? Well, you don't really have to use this limit computation because we develop all the derivative rules in Calculus 1 class. The only complexity here is that when you're taking the derivative with respect to a particular variable, the other variables stays constant. So you can treat them like constant. So let me show you what I mean. So let's take this first example, x times y cubed. And let's first take the derivative with respect to x. So if we're changing the x, y is staying constant here. So this looks like x times constant. Y cubed is a constant with respect to x. So derivative of constant times x is just that constant, right? So you don't have to use product rule here. It's just we're just using the power rule. Derivative of x is 1, and then there's a constant there. Now let's switch the roles. So we're thinking of this as now x, which is constant, times y cubed. So again, I'm just going to use the power rule. So derivative of y cubed is 3y squared, and x is just there because it's a constant. Okay. Let's look at the next one. So here, let's see. Here I can use quotient rule if I want. Yeah, let's use the quotient rule. Okay, so now remember, I'm taking the derivative with respect to x. So derivative of the bottom, sorry, no. We just have the bottom times the derivative of the top. Now, derivative of 2y with respect to x is 0 because 2y is like a constant with respect to x. Minus the top function times the derivative of the bottom. So we're taking the derivative of y plus cosine x with respect to x. So derivative of y is 0, but derivative of cosine of x is negative sine of x. Okay. I hope that made sense. Let's do derivative with respect to y. So the lower function times the derivative of the top. Now this time we're taking derivative with respect to y. So derivative of 2y is just 2 minus the top function times the derivative of the bottom function with respect to y. Derivative of y is just 1. And derivative of cosine of x is 0 because it does not depend on y. Its derivative constant is 0. Okay, I hope that made sense. Let's do this again for the next one. Okay, if I'm taking derivative with respect to x, I should use product rule here. So I'm thinking about the function x and the function rest, the sine of xy. So derivative of x is 1 times sine of xy plus x times derivative of sine. So here I have to use chain rule. Derivative of sine is cosine. And after I take the derivative of the sine part, I have to multiply by the derivative of the inside. The derivative of x times a constant is just a constant. So y goes there. Okay. Derivative with respect to y is actually a little bit easier. I don't have to use product rule here because I can think of x as a constant. So it's the constant times the derivative of sine. And then this time, I'm taking the derivative of x times y with respect to y. So derivative of y is 1 times x. Okay. I hope this makes sense. So all of the derivative rules that we learned in Calculus 1 directly transfers over to this setting. The only complication is you have to keep straight what's the variable and what gets treated like a constant. So as long as you can keep that straight with practice, that's all that's new here. But I want to know, I want to talk about what it means, what the derivative means in this multivariable setting. So graphically speaking. So in single variable calculus, you had a particular meaning. It was the slope of the tangent line to a graph of f. Well, we do have a graph. So what does it mean to be talking about the partial derivatives here? So I wanna kind of draw it, and please bear with me. It's a difficult thing to draw. So let's say I want to look at the derivative of f with respect to y variable, looking at the point AB. So let's say this is A, and the y coordinate is B. So AB, this is the point in the domain of the function itself. The actual point on the graph is going up until you hit the surface of the graph. So let's say this is the point A, B, f of AB. Okay, so I'm looking at this point, and I want to know how the height of the function changes as you move in the direction of y. So y is that direction. So what I'm thinking about is I'm fixing the x value here, and along the surface, as you move back and forth in the y direction, that is the curve it traces on the surface of the graph. Okay, so I look at the tangent line to that curve, right? So I don't know if I can draw this. Sorry, that was terrible. I hope that makes sense. So it's supposed to be tangent at that point to this surface in the direction of y, keeping the x value constant. So in this case, as the y increases, the surface is sloping downward. So this is a negative partial derivative in y direction. Okay, I hope that makes sense. So you still have the tangent slope of the tangent line. It's just that particular slice of the direction is determined by which variable you're taking the derivative with respect to. And again, we could actually also draw a picture of the partial derivative of f with respect to x at the exact same point, evaluated at AB. So if you fix the y value at B, but move in the x direction back and forth, then you're traveling the surface this way. So the slope of that tangent line is going to be the derivative um, of f with respect to x evaluated at the point AB. I hope that makes sense. So again, in this direction, as x increases, the surface is sloping downward. So uh, the, the derivative here is also negative, although they do not have to be the same, right? It could be sloping steeper in one direction over another. Okay, I hope that makes sense. So this is the graphical meaning of the partial derivatives. All right, this is where I want to end the video. I'll see you guys later.